Next up, we are going to have some fun with some low-level rootkits kind of stuff. Now, Alexandre Borges, yes. I'm doing my best here, is in all the way from Brazil, and he is a first-time speaker. So we want to give him a special recognition. So let's give him a round of applause. Have a wonderful time.
Thank you. Hello, everybody. Good afternoon. My name is Alexandre Borges. I'm a malware and security researcher at Blackstorm Security. And let's talk about Rootkits. First of all, two things. English is not my native language, so if you don't understand something, please send me an email. And these professionals deserve my sincere thank you and a deep respect for their researchers about the same theme. Let's start. Honestly, I was expecting only 10 or 12 people here. This is a table of content. I will talk about two topics, ring 0 and advanced malware, ring -2. First, rootkits ring 0. Malicious drivers have been using the same tricks every single day to infect systems. But no doubts, callback methods or kernel callback functions is a good one because it's a kind of modern rooks used by antivirus programs for monitoring and alerting the kernel models about a specific event occurrence. Kernel callback methods are a good trick to evade defenses. Kernel callback methods provide us a notification when a process, a library, and a kernel memory is mapped into memory, when a file system becomes available, when a system is going down, before a system crash, when a thread starts or ends or finishes, when a process starts or finishes, when some hash entries are modified or removed. For example, I have seen some malwares using this specific callback method, CM hash callback, for checking if their persistence entries are kept, and just an analyst or software or a programmer remove it, so the malware is able to add it back. It's a nice trick to keep the persistence. To find the number of callback methods is so easy using win-the-back, the first command there. And running a couple of commands, we have a very nice way to list the callback methods. For example, ps set create process notify routine adds a kind of list of callback routines to be called when a process is created or deleted. So in this case, it's so easy to find the number of installed callbacks, the first command at win-the-back, and a very easy intuitive command at the middle to list all the callback methods that are installed. In the last few weeks, I have seen several malwares using this specific callback method, ps set legal notify routine callback methods, to register a malicious routine that is called during the thread termination. In this case, the malware changed the keythread.lego data to provide a malicious address, and the routine redirects the execution flow to the malicious code. It's a very nice and different trick. Here we have the output from the last slide about the callback methods associated to create process. And here we have the structure of key thread and the legal data field that is changed by the malware. Windows offers different types of drivers, such as legacy drivers, filter drivers, and manufacturer drivers. All of them are developed by using our WDM or WDF frameworks. Basically, a driver is composed by one or more device objects, and each object is associated to a driver object. So, most Ring 0 malwares install filter drivers for modify aspects and behavior of existing drivers, filter and resulting of operations, add new malicious features, for example, keyloggers. The trick is almost the same. We have a driver stack, and the malware first creates an unnamed device object by using this first function, add device. And secondly, the malware adds the unnamed device object on the top of the stack by using this function IO attached device. All communications in the drive stack is done by using IRP packets. And each IRP packet is processed by a dispatch routine that's retrieved from the major function table. The IRP parameters are retrieved from the IO stack location by using this function, IO get current IP stack location. Additionally, it's possible to pass down the IRP parameters to the next layer by using IO skip current stack location, or copy them by using IO copy current IRP stack location. Alternatively, IRP packets can be passed down to the layer drive by using this specific call, IO call driver. Here we have a very nice trick. Some malwares try to pass the IRP package to the lowest driver by passing the middle of drivers, and so avoiding to be detected by monitoring tools and hooking tools. So it's a very nice and smart trick to evade defenses. Here I show you a complete picture about it. At left, we have the driver stack. At right, we have the associated device objects to each driver. Pay attention that the IO call driver function is called to pass down the IRP package to the next layer. At bottom, we have completion routines that are called in the reverse order. So the completion routine is the function that does the job. All of them are managed by the IO complete request function at right. Here we have the IRP structure composed by a static part and a dynamic part. The dynamic part is composed by IO stack locations. So each IRP is created by calling the IO allocate IRP function, and as I mentioned before, this function and the other three in your head are interesting functions to be analyzed when you reversing a malware. At the right bottom, we have the I/O stack location structure, composed by the major function. The major function holds the pointers to dispatch routines, parameters field, and completion routines field. Parameter fields depends on the major and minor functions. So, in this slide, we have its structure of the parameters fields. In the next slide, we have a complete list of IRP types. So easy. Here we have a complete relationship between the I/O stack location structure, device object structure, and driver object structure. It's a good slide to read tomorrow night. Here I show you a step-by-step investigation about a potential malicious driver named A. Borges with some commands in WinDebug. And pay attention, this specific malware uses some dispatch routines such as create, read, close, write, and device control. It's so usual to see things like that when you are analyzing malicious drivers. Here, a more complete overview showing you the relationship between the reversed code, driver object, and dispatch routines. In this slide, I started an investigation about a potential malicious filter driver by using some commands in WinDebug. Naturally, as close to the bottom of device stack occurs the infection, the more effective it is. I mean, most monitoring tools and hooking tools try to check the middle of the stack. So, if the infection happens at the bottom, you are skipping all these tools and evading the defenses. Some malwares try to intercept requests such as read and write operations by manipulating the merge function array. For example, MG device control and IRP internal control callback dispatch routines. Rootkits try to protect itself from being removed by modifying functions such as IRP, MJ, device control, and hooking requests going to the disk. Is other kind of tricks. Some malwares try to hook the driver and load routine for preventing the rootkit of being removed. Another trick. However, most malicious drivers or most malicious malwares try to avoid touching areas protected by patchguard because patchguard is so tough to circumvent. Here we have a list of protected areas by patchguard. Thanks to Alexandre by this command. Most time, malwares have been storing their payloads and configurations in encrypted hiding file systems. And additionally, they have created random device object names during the boot to associate to the special file system. Some malwares composed by executable A drivers have been using APLC, Advanced Local Procedure Call, to perform the communication between the user code in the driver code instead of using I/O control commands. Is another smart trick. Some malwares don't choose any specific driver for injection, but try to randomly pick up a driver by parsing this last structure there. Key loader data table entry. Certainly, hooking the file system access is so easy. Here, I show you a complete list of APIs. It's so easy to do that. Few malwares have been hooking this specific API, ZWCreate, for intercept all open requests sent to devices. It's a very smart trick because EVs antivirus use the same tricks. Some malwares, after infecting a system by dropping kernel drivers, try to force a reboot by calling ZW raise hard error function. Is a very special error trick. Other malwares try to use the last routine here in red. You register shutdown notification for restoring the malicious drivers in the next boot. So if you try to remove them, they back. Fortunately, most malwares have been using xallocate pool with tag function to allocate memory pool, but it's so easy to find them because we have the volatility here. We can find it by using either pro, as you already know, or execute a command and win the back. Finally, most malicious drivers have been using APC injection to inject some malicious code instead of using create remote thread. So my recommendation is to pay attention at these three lasting functions in red. Now, I'm talking about advanced malwares, basically rootkits minus ring minus 2. When we talk about ring minus 2 malwares, the context is so different. Most malwares acting in this level attack MBR, VBR, UEFI, for example. Some malwares alter the BBP BIOS parameter block to change the execution flow to another place. In this case, this kind of malware alters this last field, hiding sectors, to change it to another address and execute the malicious code instead of executing the IPL. Here we have a real case about malwares such as TDL4 or Petya, which encrypt and infect the MBR. So in this case, the trick is try to load a good MBR and a bad one in the IDA Pro and emulate them using box simulator. So I try to compare to make my analysis easier. MBR modifications and VBR modifications are effective ways to bypass KCS, kernel mode code sign policy. KCS is responsible for validating the driver signature. So there are some ways to bypass KCS. Disable it, put Windows in test mode, but in this case, secure boot must be disabled. Change the kernel memory, it's so easy. Or even trying to find a flaw in the firmware. In this case, again, secure boot must be disabled. Here, we have a real case about a Trojan banker, where the malware is put in Windows in test mode. In this case, the goal is to force in a near future to load an unsigned malicious driver. Here, I show you a more complete overview. Composed by BIOS. Here we have the boot process, composed by BIOS, MBR, VBR, boot manager, and look at the left down. There we have the WinLoad easy. Many bootkits try to attack it before load the kernel and ELAN protection. It's another smart trick to bypass defenses. Malwares have been infecting boot manager. Boot manager is responsible to switch the process execution from real mode to protect mode. So malwares have been using some interrupts to access the driver, to patch models, and load malicious drivers. At the bottom, I show you some tasks associated to WinLoad-Z. It enables the protect mode, check the model's integrity and load the Windows kernel, load several DLLs and ELAN protection, and finally, load drivers and system registry data. Therefore, integrity checking of Windows load is critical. And if it is subverted, everything falls because the integrity control doesn't exist anymore. So pay attention here. All modern protections are based on digital certificates and digital signatures. So it's critical. Most advanced rootkits, as I mentioned previously, store their payload and configuration in encrypt hidden file system by using some special opcodes. As you know, SM mode is a kind of magical mode or God mode. That's a perfect place to hide a malware. Here, I show you a first approach composed by SPI Flash, SMM, UEFI services, MBR, VBR, the OS loader, and OS. Pay attention here. Malwares can attack any block here, so you are not safe. Here is a quick reminder about the UEFI phases. So easy. Here I show you a more complete overview about the boot process composed by hardware, the UEFI phases, and things like that. Again, malwares can attack everywhere here, but we have good protection such as boot guard, UEFI secure boot, OS secure boot, and so on. Remember, the SPI Flash is composed by the scriptors, Gigabit Ethernet, Manage Engine, ACPI, and BIOS. So, for example, the boot guard, controlled by Manage Engine, is responsible for validating the boot process by flashing a public key into the Intel Manage Engine. Obviously, for a perfect working of the boot guard, the SPI flash region must be locked, and the boot guard configuration must be set and protected against SM rootkits. Here, I show you a quick picture about the boot guard blocks. Basically, each block verifies the next one. It's kind of a certificate chain. Another very interesting protection is the BIOS guard, which runs within the SMM and protects the platform against non-authorized the SPI flash, BIOS update, boot infection, and corruption. And basically, BIOS guard only allows trusted models to modify the SPI flash memory. Secure boot is responsible for protecting the entire path against bootkit infection, protects the key components during the kernel load, key drivers and important system files, and at the end, secure boot prevents any loading of strange code without a valid digital signature. Two essential items in the secure boot are the platform key. The platform key establishes a relationship between the platform owner and platform firmware, and is responsible for verifying the key exchange key. And at the bottom, key exchange key establishes a trust relationship between the platform firmware and OS. Additionally, the key exchange key verifies the authorized database, which contains authorized signing certificates and digital signatures, and forbidden database, which contains the forbidden certificates and digital signatures. Obviously, if the platform key is corrupt, everything falls because the secure boot must be or can be disabled. Unfortunately, some vendors store important secure boot settings into F5 variables. However, if some rootkit exploit these variables, secure boot can be disabled. UEFI BIOS support terse executable format. However, terse executable format doesn't support signatures. And remember what I told you. All the modern protections are based on digital signature and digital certificates. So in this case, if a rootkit is able to replace the typical PL loader by a terse executable, so secure boot can be disabled. Fortunately, new release of Windows 10 introduced a very interesting feature about SMM protections known as Windows SMM Security Mitigation Table. In Windows 10, the firmware executing SMM must be authorized and trusted by VBS. So it's an additional protection for us. SMM protection flags in Windows can be configured for your use. And here I show you some flags. Finally, I'm showing here a practical case, a real case about a customer in Brazil. In this case, the system is not protected against BIOS writing. You see, the second one, BIOS read-write permission. So it's terrible. In the same system, BIOS write enable is set. It's terrible too, because any malware can write a malicious code there. The BIOS lock enable is unset. It's terrible too, because this is a kind of notification bit. The SMM BIOS write protection is disabled. Horrible again. At the bottom, right, the protection range register are disabled too. So in this case, we have a complete exposed machine, complete exposed system. Here I'm using chipsec to perform my analysis, my checking. Here we have the flash configuration lockdown is enabled. That's okay. However, it doesn't matter because the settings protects the protection range registers which are disabled, so it doesn't matter. Here, the BIOS stop swap mode is disabled. That's okay, because in this case, it's impossible to redirect the resetting vector to a backup boot block. And so it's impossible to execute a malicious code. Finally, the SMM range is enabled. It's a good one. It's a good news. So it's impossible to access the SMM run from a non-SMM mode. My conclusion are most security professionals are not ready to analyze malicious drivers because the theory is huge and not easy, and I know that. Real customers, real world, are not aware about ring -2 threats, and they don't know how to update the firmwares. Most customers don't know how to do that. And finally, remember, all modern protections are based on the integrity. For example, digital certificates and signature. However, I leave a question here. What would happen if these algorithms were broken, for example, using quantum computation? This talk is dedicated to my wife and for you, who reserved some time to be here. Thank you for attending my talk.